Okay, so from last video we talked all about the basic design of a factorial analysis. Remember, we have main effects, we have interactions, and we're going to talk a little bit more about those interactions in this segment. Factorial analysis, just in case it wasn't clear before, it's not like you have to use a factorial model, but it is very useful for picking up interesting artifacts in the data that can only be detected when you make use of these interactions. We can do additive models, which are factorial models that only include the main effects. We're going to talk about soon why we don't really do that in practice. There are some examples where factorial models can do more harm than good. Suppose you had 3 separate catalysts. All 3 must be present in order for a reaction to go forward and produce some sort of effect. We can do a 3-factor design with 8 treatments, the combinations of each catalyst either present or absent, so those would be like indicator variables in the model. Given the above scenario, we would only get product when all 3 catalysts are present. And we learn that fact using the factorial experiment. However, with the main effect and interaction decomposition that's implicit in the factorial model, we're going to just disguise that result of the 3-way interaction that's required in order for the production. But despite that drawback, and we'll go over an example. Actually, I simulated code to show you in more detail that poor use of a factorial before, and we'll go over that in class. I think it's interesting to see that. But there are only 2 situations in which you need to use a factorial. So really pay attention to this. It's really important. When you think interaction is present or you're certain it is, or when you think interaction is absent or you're certain it is. So what does that mean? We basically need to use it almost all the time, because pretty much the kind of example on the previous slide will hardly ever happen, and more often than not we need to assume the interaction in order for us to have a more accurate analysis. When interaction is absent, a factorial is still more efficient than just analyzing study A and study B separately, because you could do that. You could just do study A, you could do another model for study B. But I would recommend, even when your interaction is non-significant, we'll see cases like that, that this factorial design is a better one to use. So our definition of interaction that Gary uses here is not based upon scientific principles or considerations, so don't get that confused. We're not talking like a chemistry lab here. We're talking about interaction in terms of statistical modeling. So the need or not for interaction in modeling a data set depends on the scale of your response. Okay, this if you think about log transforms, this makes a lot of sense. And in fact, the earliest work on interactions talked all about using these log transforms for assessing interactions. This means that data sets can look interactive on a natural scale, but additive after a transformation, especially like a log transformation. Interactions always in the context of scale. Interaction as we use it is a modeling concept and not a scientific concept. Often we might think about it scientifically, so that may not be a hard and fast rule of thumb, but it will not always have scientific meaning. The ANOVA allows us to determine whether the interaction terms in our model are significant, but it doesn't really help us understand the nature of the interaction. We really need interaction plots to do that. So we're going to take a look at some interaction plots here that I think are really interesting to help us understand the difference between treatment means that may depend on 2 or more factors. Okay, we can talk about a plot where we look at all ij combinations and then we connect the dots between adjacent means like that across the same, that share the same j, or we can do it that share the same I. I like to look at both because certain times one view will be easier to interpret than the other, even though it's the same data, same effect. The two directions, like I just said, the two directions of plot will often give very different impressions, even though it's really showing the same data. It's just about being able to understand and see and analyze that interaction. Okay, so for the example that'll be on the next slide, we have NOx emissions from dual fuel engine with the start of injection varied between 16 and 52 degrees before top of dead center. Okay, I'm not going to pretend I understand all that. I just know we're looking at emissions varied on some kind of start of injection variation. Both plots show a greater effect of fuel at low SOI, although Gary likes the first one better. So let's look at those plots. So we do see at the lower SOI, like Gary said, we see a greater effect, the mean of the NOx, a higher value. We see very much a polynomial type effect for the relationship between NOx and SOI. That is true for gas, that's line 1, and H2. Okay. Notice we could also, so notice this, we did lines that varied by fuel type. Remember, fuel and SOI were our two factors here. But on the next plot here, we vary line type by SOI, so we only see gas and H2, and I completely agree with Gary. The first one is so much easier to read than the second. We look here and there's a bunch of lines, number 1, which kind of makes it hard. They kind of are going the same direction. They're either headed down as we go from gas to H2, or they're remaining about flat. And that is consistent more or less across all soil SOI types. But we really clearly see a similar effect, although more separation up here than we see down here. So maybe there's some very slight interaction, but I wouldn't be surprised if there is none. So the third plot uses the square root of the NOx, so he did probably a variance stabilizing transformation and says that. The variability in this data is tiny relative to the mean difference, so that everything's highly significant. Okay, so let's look at that third plot. Okay, so this is with the variance stabilizing. And so remember on that first plot where I mentioned, oh, we see more variability at the low levels and less over here. Well, that got fixed here. Okay, so square root transformation of NOx, and that heterogeneity of variance is now fixed. So we see something that's very similar happening for gas as is happening for H2. And if we look, I'll have to show you the data itself, but Gary does say the variability in this data is tiny relative to mean differences, so everything was highly significant. So we see everything, even the interaction effect, being highly significant. I would say that there's a difference, there's a shift between 1 and 2. I don't see strong evidence plot-wise for interaction, and it may just be because of the fact that, like he said, the variability is so small. So let's look at another example. Freezing time of small samples of ice milk or ice cream mix using different kinds of milk and different amounts of salt. Both main effects are significant, but the interaction is not significant here. I guess this was a student project of Gary's, one of Gary's students. So rather than doing the project we're doing, they looked at making ice cream, which is fun. And maybe Gary has a point that this is a student project you can really appreciate. Let's see, we had 4 levels of milk, 4 levels of salt. Remember, this is A-1, B-1, and so then 3 times 3 gives you 9. So that's A-1 times B-1. And we do see, in fact, that interaction is not significant. And this is a nice indication of data with non-significant interaction. Look at different levels of salt, the 4 different levels of salt. We see basically the same effect of the milk type. I would have maybe ordered these differently because, to me, half and half is obviously going to be the highest fat, then 2%, then skim, then soy. And if you had reordered this, it would actually be going from very low on up as you get from lower and lower fat milk. Soy, I don't know. That has some fat, but it's also not milk fat. So lower, highest in milk fat would be best to put down here, and lowest in milk fat over here. But otherwise, the results look interesting. He put error bars on this to also make a comparison, and you can really see that if you look at the overlapping error bars, that the effect of salt doesn't really have a significant effect on a different effect on freezing time when you vary the levels of milk fat in the milk. Okay, let's take a little break here and then we'll get back to the model and parameters.